Hello and welcome. Today I want to tell you about one of the most beautiful puzzles that the world's been tragically deprived of, and I'm talking about Whodunnit by Harry Watson. So a version of this was used as part of the Road to Las Vegas challenge earlier last month. Um, but Harry's original version had some additional pieces to it, which they not unfairly decided were probably too hard for a 30-minute challenge, but they have such a beautiful resolution of the story. It's so cleverly put together. I felt like this had to be shared. So that's what I'm going to do today. So brief background on the challenge. It's mostly about encryption and decryption. So you're learning about codes and characters, which I'll tell you about in a minute, and then here's your encrypted text, and you're going to shift it along a certain amount, and that'll decrypt it. And then you decrypt longer messages. Um, and then you get toward the end into this sort of funkier stuff with really wacky Unicode messages that you have to decode into confessions of crimes which turn out to be Excel functions like Friday I committed octohex, or Tuesday I committed find, or Saturday I committed acos, and so on. Um, and that was as far as the original case got, but it was named Whodunnit, and the whole idea was that you were trying to use this cryptography, this decryption, to crack a murder. And so the final level and the few bonuses associated with that were all about cracking that murder. So before I jump into that, let me just give you a quick little bit of background. So a traditional cipher, a Caesar cipher, for example, like this one will always send letters to letters. So, if you wrap around, so like here, for example, the C shift by -3 goes back to B, goes back to A, then wraps around, goes back to Z. So you get Z test. But the advanced ciphers that come up with these crazy things, for Harry's case, don't wrap. They keep going. And so to understand that concept of keep going, we need to talk a little bit about Unicode. So Unicode, you might have heard of ASCII alternatively. It's like the super souped up big brother of ASCII. Unicode is a way um, of sort of assigning numbers to all kinds of characters. So simple version is the Unicode for the uppercase letters of the alphabet is the numbers from 65 up to 90. So there's a function unichar that converts a number into the corresponding character. There's another function unicode that converts a character back into a number. So you can go either way with that. But so Unicode has codes for the uppercase letters, codes for the lowercase letters, codes for each of the digits, but it has a massively wide. So these are all ASCII characters as well. So ASCII goes up to I think 255 or 256. Unicode goes way beyond that and has things like all the dice codes, all the chess pieces are Unicode codes, all the card suits are Unicode codes, all of Braille is Unicode codes. Dominoes are Unicode codes, various, well, I think all, but certainly many Chinese characters, Arabic characters, Hebrew characters, and more recently, lots of emojis are all Unicode characters. And so the idea is that, instead of saying, well, we'll shift along by 3 letters, and that'll take my C to a D, E, F, you might say we'll shift along by 128,000 letters, and that's going to turn my C into an emoji. And that the result of that is that you can end up with these, totally baffling looking messages here. So we're going to want to be encrypting and decrypting under these weird rules a lot. So I'm just going to start by making a quick lambda to handle that. So I've got a few inputs here. I've got some test text. I've got a shift, and sorry, I should explain the concept of an long shift as well. So in Harry's world, it's not just a single shift of, say, add 1,000 to the Unicode character. There's also this concept of an long shift, which basically means the shift grows the further into the message you get. So suppose your shift was 1,500 and your long shift was 25, then the first the first character is shifted by 1,500, the next one by 1,525, then 1,550, 1,575, 1,600, and so on. So let's do some quick lambdas for this. First, we're going to split this into letters. It's a pretty standard trick, so we'll say mid of this, sequence len of this by 1. So sequence of len here is just going to give us the numbers 1, 2, 3 up to 13, because there are 13 characters in here, and then mid of this 1, 1 is going to say give me the the character starting in position 1 for one character, then starting in position 2 for one character, and so on. So it gives you the set of letters, and that's actually going to be a useful one. I've got this as a sort of saved lambda anyway, but so I'm going to mark this as input, and then I'm going to say, I'm going to pull up a robot command, just make it easier, say save lambda as, and I will say yes, that is what I want, and I'm going to call it letters, and save that. And then let's keep going. So we'll do codes, will be unicode of that. Then the shift will be sequence of len of this, starting from 1500 and in steps of 25. So in other words, the first one is going to get shifted by 1500, then 1525, and then so on. So then we'll have new characters will be unichar of this plus this. And that gives us all these weird things, and if I make that 1000 instead, I get a different set, and so on. Make that 20 instead, they move differently. So then the output is going to be concat of that. So this is my encrypted text. I'm going to mark those as inputs as well, but I also want to add a couple more optional parameters here to allow for a couple of other situations. So two things. One is I'm currently using this to encrypt, but if I do the shift in the opposite direction, then I would be decrypting. So I want to have the option to decrypt. Now, the way I like to write my lambdas is with a default behavior so that I only have to put in the minimum number of parameters. So my default behavior is going to be encrypt, and then my alternative behavior is going to be decrypt. So if this is omitted, it's going to be encrypt, and if it's a 1, it's going to be decrypt. So how can I do that? Well, I could multiply this by 1 minus 2 times this. And that way, if I leave this blank, 2 times that is 0, and 1 minus that is 1. So it's just multiplied by 1, which changes nothing. But if I make it a 1, then it shifts the sign on that and makes it negative. Now this is erroring out because if you subtract 1000 from 84, you get a negative number, and there are no Unicode characters for negative numbers, but that's fine because we'll only use this if we have things with big Unicodes here. And then the second thing is that for some of the easier questions, you don't encrypt spaces and numbers. So again, I'm going to have an optional thing here, and what I'm going to say is, let's see, I'll say if we're encrypting space and numbers, and this is a space or a number, then don't encrypt. Otherwise, then don't shift. So shift, add 0 for the shift. Otherwise, add the shift. And so my test for is it a space or a number? Well, a space is a Unicode 32, and numbers are Unicode 48 to 57, and text starts from 65. So I'm just going to say, as my test, codes is less than 65. And then if I say skip spaces and numbers, you should see, yep, this is now still a space, and this is still a space, and these are still numbers, and everything else is getting encrypted. So that's the setup I want. Now let's save lambda as. And I'm going to call it encrypt, I guess. Oh, sorry, first I want to mark both of these as optional. And so if I just mark the first one, it applies the same to the second one, which makes sense because you want all your optional stuff at the end, and I'll call that encrypt. And so now I can say encrypt of this with this shift and this along. And if I want to skip spaces, I can do that. And then I can encrypt if I can spell it. This with this shift, this along, but now decrypt, and it gets me back my plain text. So now I've got two handy little lambdas that I can bring with me. Okay, so now let's get into some of the solving. So in my previous, I did a video on the sort of public version of this case that covers kind of everything up to level 6 in Harry's case, which was level 7 in the original case. So let's start by taking a look at that. First, I'm going to show you what I did on the day, which was messy but manageable. So the idea here is that you've got all of these messages were sent by a certain person to a certain person on a certain day. So there's a grid of the big shift is a function of who was the sender and who was the receiver. So there's this grid of possible big shifts. And then the along shift, the extra bit that adds for each character is a function of the day of the week. So if they sent it on Monday, there's no along shift. If they sent it on Tuesday, there's an along shift of 1, 2, 3, 4, 5, 6, etc. So the way I did it was just I built a big grid of these are all the possible combinations of the 380 distinct big shifts and the 7 distinct days. So I get 2,660 possible combinations. And for each one of those, I said, okay, this is the big shift, this is the along shift, and we're told that the correspondence begins with the first word is the day of the week on which it was written. So you can see in the decrypted form, they're all like Friday I committed, Tuesday I did, Saturday I was, etc. So what I did was say, okay, with this big shift and this along shift, what does Monday become? And that tells me, and again, because an along shift of 0 only happens on Monday, an along shift of 1 only happens on Tuesday. So there are these 2,660 possible words with which the encrypted message could start, and each one corresponds to a combination of these. So all I did was take the text before that, look it up to give me my shift and my along shift. I can look that number up to say, okay, 10, 5, 5, 6. Oops, all right. Means the message has to have come from Felix. And this is the decrypted message. And then you just have to kind of look it up to say, okay, so for oct to hex, the person confessing to oct to hex is Felix. And if you have a sharp eye, you'll notice that this is hard-coded, whereas the rest of these are formulas. And that's because the formula that I used on the day, I didn't even read the thing that said about spaces and numbers being skipped. But I saw that it was throwing an error on the spaces, so I just said if error space, which meant that this didn't give me oct2 hex, it just gave me oct space hex. And similarly down here, dec space hex. So I just went through and, I'll show you. I just copy value pasted those and changed it to a 2 so that I could match it. But that got that level out, but in a very, very brute forcey way. Like, let's test 2,600 different possible things. There were a few other, call them, medium smarter ways to tackle this that were at least much, much more efficient. So, for example, you could say, consider the first character. The first character is only encrypted by the big shift and not by the thingy thing, and not by the along shift. So you could say that first character, knowing that you're starting with a weekday, has to be one of M, T, W, F, and S. So you could say unicode of this. If you say unicode of a whole text, it just applies to the first character. That's how it works. So the first character there is 10,626. You say that minus unicode of M, T, W. I'm going to do them all, just I'll show you why in a minute, but S. So I'll include the repeats, SS. So these are your possible along shifts, and I suspect in most cases you could say countifs on this grid of shifts. Probably most of those aren't even there. So yeah, so in this case there's only one possible big shift, and then once you apply that big shift, where you could say first character of this, unicode of the first character of this minus the one that's valid gives you that, and then char or unichar of that tells you it's an F. So it's F means it's a Friday, means the shift has to be 4. So you could kind of, by doing some casework, you could get a lot more efficient. But you're still looking at different possibilities, and maybe under a different shift this could be mapped to a different letter and so on. So there's still some kind of ambiguity there. The kind of big brain approach to this that somebody showed me after the fact, I don't claim to have figured this one out myself, was to use the fact that there's a sort of pattern in the end of the words. So in other words, every day of the week ends with DAY, and you can use that to your advantage. So you can say, let's just give ourselves a little more space. So you can say, text before this space to give you the word, and then you can say right of that by 2 and 1. That'll give you the last 2 characters and the last 1 character. There's a little sneaky trick I picked up from Bo. You might think you'd have to use mid and do some careful adjustments to get the last 2 characters, or take the right 2 and split it or something. But if what you want to do is apply Unicode to it, then again, remember Unicode only takes the first character, so it only points to the second last one here and to the last one here, so that works absolutely fine. So you can take that. So these have to be the encryption of the letters A and Y. So what we can do is subtract off the Unicode of A and Y, and this is the shift being applied to A and to Y. And so that shift is the base shift plus a certain number of times the along shift here, and 1 more time the along shift here. So in other words, the difference between these two is going to be the along shift. So you can say this times, so make the first one negative, the second one positive, and then sum them up. And that will give you, with no casework, no anything, that will give you the along shift. And then once you have the along shift, you can convert that into a day. So I'll just do the shortcut way, which is because the days are in order. I'll just show you here. So if you say day of that, not what I meant. If you say text of these day, it needs to be uppercase, but anyway, you can see that gives it to you kind of off by 1. So a 2, if you convert a 2 into a day, like if I just went to custom format and said day, 2 is a Monday. So if I just add 2 to each of these, convert them, that gives me the text. Or you could just do a lookup here and return from here. Either's fine. Point is, you get your day, and then your big shift is just the Unicode of the first character of this minus the Unicode of the first character of that. And again, you don't need to extract the first character. You can just say Unicode of the whole thing, and it'll apply to the first character only. So Unicode of this minus Unicode of that, and that's your that is your big shift, and that's your long shift, extracted nice and easily. And then let me just grab my, oops, don't mean to show you that. I'll have to cut that out. Then I just grab my lambdas over here and paste it in here, and I want to decrypt this using this shift and this along shift, decrypt, and skipping spaces and numbers, and there we have it. So this is one where, like, it's very brute forceable, and then there's lots of ways that you can kind of refine the brute force. You can think about, how many characters are in that first word. Well, some weekdays have a unique, I think Wednesday is the only 9-letter day, that kind of thing. You can make kind of little bits and steps, but this method, based on the fact that it always ends in A and Y, is sort of by far the neater one. So now we've got the setup. Let's get into the really hard case. So I'm going to start here. So in the very hard case, instead of having this neat, here's 30 individual messages, we have one big blob. This is all just one big merged cell here. And this is a combination of over 100 different messages that contain information about where people were at different times. So the original level 7, it gives you some information about how this is encoded, which I'll go through in a minute, and it asks you to figure out, for a given person and a given day, what room was that person in. And then the bonuses take you through actually solving the murder. So first, let's go through the encryption. So for this encryption, I mentioned before that numbers and spaces were not encrypted. In this version, they are. All characters are encrypted. Spaces are replaced with underscores. I think the idea there was that a space is a Unicode 32, which is sort of a good shift outside the range of the alphabet, and so it might have been easier to pick out, whereas an underscore is 95, which is right next to the letters. So spaces are replaced with that. Every correspondence ends with 5 underscores, except, again, those 5 underscores are encrypted. So somewhere in here, there's an encrypted version of 5 underscores. Let's say it's here, and then a new message begins. So again, I'm first going to show you what I did live, because I got to play this case live as part of a little speedrun challenge on Jack's channel, which I encourage you to check out. So first thing, I split it into characters, as you would expect, and took the unicodes of those. And then, similar to what I mentioned before, we're looking for, if we take the difference between consecutive characters, then we're canceling out the, well, it'll be easier to show you here. So I should have new codes. Let's just grab that. Just do this plus this. So I mentioned that if we take a couple of these and subtract off a couple of the unencrypted characters, and then take the difference, that's going to give us the size of the along shift. But if we go one step further, if we take a few of these, subtract off a few of these, then take this minus this, and this minus this. That's right. And if we don't subtract off, if we just take the encrypted characters, take the difference, and then take the difference again, we're basically eliminating the two shifts. So let's just show you here. Here's the unencrypted version. Let me just make sure I have the same 3 characters. Yes. So here, this and this differ by 20, and this differ by 20, because when you take the difference of these two, the big shift cancels out. So this is, the base value plus the big shift plus some number of steps of the along shift. And this is the same thing, a different base value plus the big shift plus one more step of the along shift. So when you take the difference, the big shift cancels, and you're left with the difference in the underlying characters plus the along shift. And here you're just left with the difference in the underlying characters. So the difference between these is exactly the along shift. And similarly, the difference between these is exactly the along shift. But so if I take the difference a second time, the extra step of the along shift cancels out, because this is the base difference plus 20, this is the base difference plus 20, so the difference of those is minus 13, which is the same as the difference in the unencrypted text. So I don't know how much that's kind of clear to me. I don't know how clear it is to people who are less mathematically inclined, but the idea is that if I take, let's just not just do these 3, but let's do, I don't have it here. Let's import. I have a little function that just takes the difference between consecutive terms. So here, the 101 minus 84 is 17, 115 minus 101 is 14, and so on down. And so if I apply that twice here, and then apply it twice to the encrypted version, you'll see that we get the same pattern in both. And so what that means is, if there is something that is in the encrypted text, like 5 consecutive underscores, you can look for the signature of that. And of course, the signature, the difference between 95 and 95 and 95 and 95 is just going to be 0, because there is no difference. And so what we're looking for here is a place where the double difference is a bunch of consecutive zeros, just like this. So this is kind of referencing to these 3. So this whole section, it's going up in steps of 6. So what you're seeing is that the sort of shift, the along shift is 6, and the underlying character is 95. And so I used that to identify, okay, if 3 consecutive ones of these are 0, that means you've got 5 underscore, or 5 of the same character, but let's assume that must be an underscore in a row. That means that's the start of a new message. So then I had a scan to say, okay, what is my message number? Start at 1, and whenever we start a new message, go on to the new message. And then I did a group by on that to say, by these labels, the message number, on these characters, concat. So now I have my full set of 157 messages. And up to there, I thought I handled it pretty well, and then after that, I did not handle it quite as well. But so the idea I had in my head was, okay, I want to decrypt this, and I know that each one of these mentions a room. So here's the set of 16 rooms. So the idea with this thing, that the pattern of double differences is the same in the plain text and the encrypted text, means that if there's a word that you know is in there somewhere, say atrium, for example, then you can, let's just do this, say letters of atrium, and then let's take code of that. Then you can say diff of diff. I want to take the double difference of that, and you get -53, -7, 21, 20, which I've just encoded like this. And the idea here is any time that atrium appears in a text encrypted in this way, whatever the shift is, whatever the along shift is, this pattern will appear in the list of double differences. And so we just encode it in this way so that we can search for it. So we say, okay, here is the signature of the whole message, and you can see all the zeros at the end because it ends in 5 consecutive underscores. And then we just said, okay, if any of these appears in there, then give me the room. And so that told me, okay, this is the greenhouse because that's the only one whose pattern appears in there. And then I can use that to figure out where in here the word greenhouse occurs. That's why I have these kind of formatted as fixed length, so that I can say, okay, if this string begins in position, whatever it was, let's see, that begins in position 61, and each character is encoded as 4 characters, meaning a minus in 2 digits or 3 digits and a delimiter, then starting in 61 will mean ending in 64 will mean it's character number 16. And then I could extract, okay, these are the characters starting from 16, 17, 18 in the encrypted text, in the decrypted text, and then I could take the unicode of all those, take the difference, and figure out, okay, so that means it's a shift of 6, an along shift of 6, a big shift of that, and then I could decrypt the location. And that was enough to answer, albeit a little messily, to answer this question, because I could pull out, okay, for this person, for this day, what does the message say? And you could figure out the person was a function of the big shift, because again, the big shift depends on who is sending the message to who from here. And the weekday was a function of the along shift, same as before. So Monday was 0 shift, Tuesday was 1 shift, and so on. So you could say, okay, this person, this day, has this message, and then you just have to strip out that piece, which I did by a double text split. So let me just very quickly show you that. So you can text split this message on the list of all the rooms. So atrium, billiard room, da 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 da. So that will split on Flower Garden. So you get, here's the text that comes before that, here's the text that comes after that, and then you split the original message on each of these, and the only piece that's left is Flower Garden, or is the room that you're in. So that let me solve level 7 in a rush, but it did not let me, I mean, I didn't have to because I only had to do level 7, but it left me with a bunch of messages that were not successfully decrypted, because there's a bunch of messages where people say where they are, but then there are other messages that relate to clues for the murder. So now let's take a clean, this is not the clean file, where is a clean file? This is the clean file. I'm just gonna grab the answers from here because I'll need it for one of the bonuses. This has changed, never mind. All right, ignore that. So now let's do a slightly cleaner solve of level 7. So have I got my lambdas in here? No, I haven't. Let's go grab those. Just a couple that I did here. This one. So then I want letters of that, and I want unicode of that, and I want diff. Oh, sorry, I didn't import diff. Let's get diff. Let's do diff of this, and then let's do and this equals 0. Minus minus. So then we'll do scan 1, this array sum, and then we'll do our group by. Let's down one, group by this, and these characters, and concat, and I want no totals. No, sorry, 0. Did I do it wrong? Oh, yes I did. There we go. Okay, so what I missed when I was trying to decrypt it based on the room was that, like I said, anything that didn't mention a room was not decryptable that way. What I missed was that I was looking for the sort of signature of a room. I should have just been looking for the much simpler signature of 5 consecutive underscores. So, sorry, where are we going? Let's come back here. What I really should have done is right of this by 1, 2. These last, sorry, by 2, 1. These last two characters are the encryption of an underscore with different shifts and different long shifts. So I can do the same trick as before. I can subtract off the unencrypted value, which is 95 or code of underscore. Code, unicode. What? Oh, sorry. Yeah. Because before I can subtract anything from it, I need to have the unicode of it, not the text. Then we can subtract off code of underscore. I get that, and then same as before, we can say we're going to multiply this by minus 1, 1, and sum it up. In other words, take the difference, and there's my along shift. So that's my along. Then I can get my day is going to be text of this plus 2. Okay. Then my shift, I can say unicode of right of this. So take the last character of that. Then that is going to be the sum of the base code, which is 95, plus the big shift plus some number of the along shift. And what is that number? Well, position 1 has 0 along shift, position 2 has 1 along shift. So if there's n characters here, then position n has n minus 1 along shifts. So it's going to be length of this message minus 1 times the along shift, and that's going to leave you with the big shift. And then we need to know the sender, and that we can just do concat if this is equal to this lock, then give us this lock, otherwise blank. So now we have our day and our sender, we have our shift and our long shift, so then we can get our message, and that will be encrypt of this text with this shift, this along shift, and we want to decrypt. And here we have my location is greenhouse, and that works fine for the ones that I was able to do before, but it also works for the ones that do not contain a room, which say things like I saw the murder and I saw nothing. So now let's go to the bonuses where we actually crack the case. And this is where I just think it goes from being a nice, tricky puzzle to being just really beautifully put together. So now we're going to solve the murder. We're going to figure out who was killed, who killed them, when it happened, and where it happened, all from these messages. So first thing, the murder victim is the only person not to send any correspondence on the day of the murder or subsequent days. Who was the murder victim? So we can come over here, and lots of ways to do this, but I'm going to pivot by. Our row fields are going to be the senders. Our column fields are going to be the along shift. You could take the day, but the days don't come out in order in a pivot table, which is not ideal. And then we can just take any other field as the values, and we'll just take a row count. And that will tell us on 0 shift, which is Monday, all 20 people sent messages. On 1 shift, which is Tuesday, all 20 people sent messages, and so on along, until we get to 5 shift, which is Saturday. Everybody sent an extra message, because this is the day that also has the messages about I saw the murder or I saw nothing, except for Felix, who does not send a message because he is dead. So our murder victim is Felix. Next question. What room did the murder take place in? Consider the level 7 correspondence outlining who witnessed the murder. So here, this is where the layout of the rooms is relevant. A person can see the room they're in and the rooms touching them up, down, left, and right, but not diagonally. For example, if you're in the greenhouse, you can see the croquet lawn, the flower garden, the hallway, and the kitchen, but you can't see the billiards room, the jetty, the library, the drawing room, or the Excel room that's 2 away, or the orangery that's 2 away. And in the level 7 correspondence, everyone tells the truth about where they are on each day, including the murderer. So we need to figure out first we need to figure out who saw the murder, and then we need to figure out where they were on Saturday. So first, we're going to filter this, the list of senders, where I guess we'll say regex test. We just want to know, does this contain the word murder? So regex test that on the pattern murder, case insensitive, just to be safe. So these are the 5 people who witnessed the murder, and now I want to know where each of those people was on Saturday. So I'm going to say filter again. I'm going to filter, oh, sorry, I haven't actually extracted the rooms from here, so let's do that quickly. Room, and again, we could use the text split trick that I used before, but it's actually neater to do regex extract from this, and the pattern is going to be, so the pattern you can use if you want to test like A or B is something like this. You have brackets for a capture group and then just A or B. So what I want in here is the list of rooms separated by pipes, and I can do that with text join. So I'm going to say text join on a pipe character, which means or in regex, the list of rooms. And let's just drop this piece for a second so you can see what that looks like. So here's my test. It's going to be atrium or billiards room or croquet lawn, etc., etc. So I want to regex extract that from there. And that's going to tell me, oh, sorry, that's not going to tell me anything because I didn't lock. So let's lock and try again. And actually, I don't know, this might, will this work as an array? I think it will. Yes, it will. So again, these don't have any room, which is fine, but these all do. So now I want to see for those 5 people, what rooms were they in on Saturday? And I guess I'm going to wrap this in an if error just in case that breaks anything. If error. So I want to filter the room, lock where this is equal to the name, lock times day is equal to Saturday. Oh, right, and that's also including the blank. Fine. So times room. Actually, I don't even need to times. I can just cut the two together because one of them is an empty string. So Grace was in the hallway, Clara, Amelia, and David were in the flower garden, and Henry was on the croquet lawn. So there's the hallway, there's the flower garden, there's the croquet lawn, which means that if they all saw the murder from there, the murder took place in the greenhouse, which I think was the question. Yes, what room did the murder take place in? The answer is the greenhouse. And finally, the question is, who is the murderer, and how many crimes did they commit in total, including the murder across levels 6 and 7? So this is where I should have, oh, I just noticed there's a comment here. Give them a hard one here. So I'm just going to fill in the answers for level 6 because I showed you the solve approach, but sorry, it didn't need an equals there. Just because it's relevant for answering there, but the logic is the same as the other one I showed you. Okay, so now, who committed the murder? We need to know who was in the greenhouse on the Saturday. So greenhouse, Saturday. We're going to filter the names where the room and the day equals the room and the day. And we get Emily. So Emily killed Felix in the greenhouse on Saturday. And then the other question is how many crimes she committed. So in level 7, she committed 1 crime, which is murder. And in level 6, she committed 2 other crimes, which is M-unit and car. And I'll leave it up to you to decide which of those 3 crimes is the most heinous. So the answer here is Emily 3. So, like I said, to me, this is just such a beautiful idea that, you know, you like you solve the public version, and it's, in a sense, it's an exercise, right? Like it's a challenge, but it's an exercise of like, okay, so we're gonna go through, we're gonna encrypt this, we're gonna decrypt that, and in this version, there's just such a beautiful story because, from this big blob of text, you turn that into this structure of, okay, different people are telling you where they are, and then it tells you, okay, you can use that to figure out who stopped sending messages and therefore who was killed. You can use it to figure out where witnesses were and what they were able to see. And it all ties back into, you can figure out who killed who, where, and when. I just think it's really clever. I think it's really beautiful. So hats off to Harry on a great piece of work. I'm a little sad the world didn't get to see this case because it is a great piece of work. Anyway, that's all I got for today. Thanks for watching. See you next time.